This is lesson 7.7, exponential growth and decay. Your objective is to model exponential growth and decay. Some vocabulary. Exponential growth is a situation modeled with a function of the form y equals ab to the x power, where a is greater than 0 and b is greater than 1. The growth factor is 1 plus the percent rate of change for an exponential growth situation. Compound interest. This is interest paid on both the principal and the interest that has already been paid. Exponential decay. A situation modeled with a function of the form y equals a times b to the x power, where a is greater than 0 and b is greater than 0 but less than 1. Decay factor is 1 minus the percent rate of change, expressed as a decimal for an exponential decay situation. Exponential growth. An exponential function can model growth or decay of an initial amount. Exponential growth can be modeled with the function y equals a times b to the x power, where a is greater than 0 and b is greater than 1. The base b is the growth factor, which equals 1 plus the percent rate of change expressed as a decimal. So a is the initial amount, the beginning amount, when x is equal to 0. B is the base, which is greater than 1. N is the growth factor, and x is our exponent. Here's a sample of a graph of exponential growth. Problem 1. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? So first we need to relate. We're going to use an exponential function because this is an exponential growth model. So we're going to use the formula y equals a times b to the x power. We're going to define that x equals the number of years after 2005. We're going to allow y to equal the annual amount spent at restaurants. And a is going to equal the initial amount spent in billions of dollars. And b will be our growth factor, which in this case, because it's increasing at 7% each year, we have to do 1 plus 0.07, which is the decimal form of 7%, and that'll equal 1.07. So our growth factor is 1.07. So first we need to write our equation. Y, which is the amount that we're trying to look for, equals 360, which is going to represent the billions of dollars spent initially in 2005 times 1.07 to the x power, our growth factor. Use the equation to predict the annual spending in 2015. Well, from 2015 to 2005, that's been 10 years that has passed, so we're going to substitute that for x. And when we do our calculations, we end up with 708. However, because we only used 360 instead of 360 billion, we have to remember that 708 is going to represent $708 billion that will be spent in 2015 if this trend continues. Compound interest. When a bank pays interest on both the principal and the interest an account has already earned, the bank is paying compound interest. Compound interest is an example of exponential growth. You can use the following formula to find the balance of an account that earns compound interest. So this would be an example would be like a savings account. So here's the formula. A equals P times the quantity 1 plus R over N to the N times T power. So A is going to represent the balance that you will have. P represents the principal or the initial deposit, how much you originally put in the account. R equals the annual interest rate, which we have to express as a decimal. N is the number of times interest is compounded per year. and t represents the time in years. So let's try to do a problem. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? So we're going to use that formula. A is what we're looking for. The principal amount was $2,000. The rate of the interest is 0.045, which is the decimal form of 4.5%. N equals 4 because the interest is compounded quarterly, which means 4 times a year. And t is going to equal 18 since we're looking for the balance after 18 years. So you need to substitute all your values into the formula. And when you do your calculations, the account will be, the balance will be $4,475.53 after 18 years. Exponential decay. The function y equals a times b to the x power can model exponential decay as well as exponential growth. In both cases, b is determined by the percent rate of change. The value of b tells if the equation models exponential growth or decay. Exponential decay can be modeled by the function y equals a times b to the x power, where a is greater than 0 and b has to be between 0 and 1. The base b is the decay factor, which equals 1 minus the percent rate of change, expressed as a decimal. So again, we have a, which is the initial amount when x is equal to 0, b is the base of the decay factor, and x represents our exponent. And this is a graph of an exponential decay function. Here's a problem modeling exponential decay. The kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases by 11.5%. What is the approximate pressure at an altitude of 3,000 meters? So we have to recognize that this is an exponential decay model, so we're going to use this equation. We need to define that x equals the altitude in thousands of meters. We're going to let y equal the atmospheric pressure in kilopascals. We're going to let a represent the initial pressure in kilopascals, which is 101, and b is going to be our decay factor. Now, the pressure is decreasing by 11.5%, which is 0.115 as a decimal, but we need to subtract that as from 1, so our decay factor is 0.885. So our equation is now going to look like y equals 101 times 0.885 to the x power. Now, we're trying to figure out what the pressure will be when the altitude is 3,000 meters. Since the meters are going to be in the thousands, we already said that it's going to be measured in thousands, so we're only taking the 3 instead of writing 3,000. We'll substitute that for x, and when we do our calculations, we have 70, which will be our 70 kilopascals. Here are some sample problems. What is the growth factor in the equation y equals 34 times 4 to the x power? Here, the growth factor is 4, which is our b value. What is the initial amount in the function y equals 15 times 3 to the x power? Remember, a represents our initial amount, so 15 is going to be our initial amount. And what is the decay factor in the function y equals 17 times 0.2 to the x power? Well, b is going to represent our decay factor, and it is also less than 1 but greater than 0. Here's a word problem. Suppose your friend's parents invest $20,000 in an account paying 5% interest compounded annually. What will the balance be after 10 years? So we're going to use the compound interest formula. We're looking for A. Our principal amount is $20,000. And we're going to do 1 plus, our rate is 0.05, our percent as a decimal. N represents the number of times interest is compounded per year. And because it's compounded annually, it's only being compounded once. So R over N, or 0.05 over 1, would just be 0.05. N, again, is 1, and our T will be 10 years. And this will be 20,000 times 1.05 to the 10th power, which equals 20,000. Oy, sorry guys, my handwriting is getting messy. And rounded, it's going to be 1.6288946. And when we multiply that by 20,000, we will get $32,577.89. So that is how much you will have in your account after 10 years if you invest $20,000 into a 5% interest account.